Welcome to the deep dive. This is where we cut through all the noise, look at the amazing sources you share, and pull out the really key insights for you. And today, wow, we are heading into territory that really makes you question, the basics of reality. What if the rules for the universe's tiniest bits aren't quite what we learned? Our mission today: unpack this really stunning new discovery about exotic particles. They seem to bend the rules we thought were solid, and they've been seen for the first time in a, well, frankly, surprising place. It's quantum physics right at the edge.
Okay, so let's just set the scene a bit. You probably remember the basics. Our universe is built from, fundamentally, two kinds of particles. You've got your fermions, think electrons, quarks. They're the building blocks of matter itself.
Right, the stuff things are made of.
Exactly. And then you have the bosons. These are the force carriers. Photons carrying light, gluons holding atomic nuclei together, that kind of thing.
And it's not just what they do, is it? They have these really distinct quantum rules, especially about swapping places. Like if you swap two identical fermions, their quantum description gets this mathematical twist, a phase of pi, they call it.
A minus sign, essentially.
Yeah, and that little minus sign is huge, right? It's why two fermions can't be in the same quantum state, the Pauli exclusion principle. It shapes the periodic table, explains why matter takes up space.
It's fundamental to structure. Bosons, though, they don't care. Swap them, nothing changes in their phase. That's why they can all pile into the same state, like in lasers or superfluids.
Okay, so two clear categories: matter stuff, force stuff. Fermions, bosons, simple enough.
Well, it was seemingly simple, but now we're looking at something that complicates that picture. Researchers are dealing with a different kind of entity. These things are called anyons, and they just don't fit neatly into the fermion or boson box. Their quantum behavior is genuinely somewhere in between.
In between, how does that work?
It's about that phase shift when you swap them. For fermions, it's pi, that minus sign. For bosons, it's zero, no change. For anyons, it's not fixed. It can be any value between 0 and pi. It's a continuous spectrum of possibility.
Okay, hold on. So these aren't like new fundamental Lego bricks floating around?
No, not exactly. That's a key point. Anyons aren't fundamental particles in the same way electrons or photons are. They emerge as collective behaviors, excitations within specific, quite exotic states of matter. Think of it like sound waves in a solid. A phonon, a particle of sound, isn't fundamental. It's a collective vibration of the atoms acting like a particle. Any's are kind of analogous, but quantum mechanical.
Ah, okay. Like ripples acting like things. And hadn't scientists seen these anyons before?
They had, yes. But the crucial thing was those observations were always in two-dimensional systems, like in super thin films of material or sheets of graphene.
Right. Flatland physics, basically.
Pretty much, which led to this big question hanging out there for years.
Yeah.
Okay, they exist in 2D, but could you possibly get anyonic behavior in just one dimension, along a line?
And the answer from this new research is yes.
A definite yes. And that's the breakthrough we're digging into. Scientists have actually observed clear signs of NEMs in a one-dimensional ultracold gas. That's the stunning first.
Wow. Okay, one dimension. How do you even set that up?
Well, it takes incredible control. And this wasn't just one lab figuring it out in isolation. It was a really impressive international effort. You had teams collaborating from the University of Innsbruck in Austria, Université Paris-Saclay in France, and Université Libre de Bruxelles in Belgium. Real teamwork pushing the frontiers.
So how did they actually see these 1D anyons? It sounds incredibly tricky.
It is. What they did was ingenious, really. They started with a gas of bosons cooled down to near absolute zero, just unbelievably cold.
Okay, super cold boson gas.
And they confined it very tightly so it could essentially only move along one dimension, like beads on a string.
Got it. A 1D quantum gas.
Then they carefully injected a different kind of atom, what they call a mobile impurity. Think of it as a single, identifiable probe atom.
And they just watched it.
They did more than watch. They gave it a little push, accelerated it, and then meticulously tracked how it moved through and interacted with that 1D boson gas. By analyzing how the impurity's motion was affected by the gas particles it encountered, they could deduce the quantum statistics governing those interactions. And that's where they saw it, the unmistakable signs of anyonic behavior.
That's incredibly clever, using one atom to probe the collective quantum weirdness of the whole gas.
Exactly.
Yeah.
And the results were really clear. One of the lead authors, Sudip Dadar, put it very well. He said, what's remarkable is that we can dial in the statistical phase continuously.
Dial it in? You mean control it?
Yes, allowing us to smoothly transition from bosonic to fermionic behavior. This represents a fundamental advance in our ability to engineer exotic quantum states.
Whoa. So they didn't just see anyons, they showed they could basically tune how anyonic the interactions were, like turning a knob between boson and fermion.
Precisely. Like a quantum dimmer switch for particle statistics. And the theory matched beautifully. Bo-Tal Wang, the theorist on the team, he confirmed their modeling work. Our modeling directly reflects this phase and allows us to capture the experimental results very well in our computer simulations.
So the math checks out perfectly with what they saw. That's always reassuring in physics.
It absolutely is. Theory and experiment hand in hand.
Okay, this is fascinating fundamental physics, seeing particles behave in between. But so what? Why does observing this in 1D really matter beyond, being cool quantum mechanics?
Right. Fair question. It matters a lot, actually. First, just on the fundamental side, having this elegantly simple setup, a 1D gas, gives scientists a new, highly controllable playground for studying anyons. It's much easier to manipulate and probe than some complex 2D materials.
Okay, a better lab for studying weird particles. Makes sense.
But the really exciting part is the potential application. Certain types of anyons, particularly non-abelian anyons, which have even richer properties.
Uh-oh, sounds complicated.
They are. But these non-abelian anyons are predicted to be the key ingredient for topological quantum computing.
Topological quantum computing. I've heard that term. That's supposed to be a more robust way to build quantum computers, right?
Exactly. Today's quantum computers are incredibly fragile. Tiny bits of noise from the environment, heat, vibrations, stray fields, can easily mess up the quantum states, causing errors. It's called decoherence, and it's a massive headache.
Yeah, keeping qubits stable is the big challenge.
Well, topological quantum computing proposes a revolutionary solution. Instead of storing quantum information in the state of a single particle, you store it in the collective topological properties of a system of anyons. Think of it like braiding ropes. The information is encoded in how the anyons are braided around each other in space-time. And crucially, that braiding pattern is robust. You can jiggle the ropes quite a bit, but the overall braid remains the same unless you actually cut or unbraid them.
Ah, so the information is protected by the fundamental shape, the topology, not just a delicate single state.
Precisely. It makes the quantum information inherently resistant to local noise and errors. It's like built-in error correction.
Okay, that would be a game changer. And this 1D enyon discovery helps pave the way.
It's a significant step. While these specific anyons observed might not be the exact type needed for fault-tolerant quantum computers yet, proving you can create and control anyonic statistics in such a clean, tunable 1D system. That's huge. It opens doors to exploring different types of anyons and potentially engineering the ones needed for topological qubits. It moves the whole field forward from pure theory toward something potentially practical.
So this discovery really does shed new light on exotic quantum matter and points towards potentially powerful future technologies.
Definitely. It's a pivotal moment in exploring these strange corners of the quantum world. And for those interested, the detailed work is published in Nature.
Fantastic. Okay, so let's just quickly recap what we've unpacked in this deep dive. We've gone from the basic building blocks, fermions and bosons, to discovering this third category, anyons, that live in between. And crucially, scientists have now seen them and even controlled their behavior in a simple one-dimensional system for the first time. It's not just expanding our fundamental physics textbook, it's genuinely pointing towards radical new ways to compute and handle information. It really is like finding a new color we didn't know existed.
It is. It highlights just how weird and wonderful the quantum world is, that particles don't have to stick to just two statistical rules. And observing it in 1D, controlling that in-betweenness, is just a remarkable testament to experimental ingenuity. It shows there's still so much fundamental stuff out there waiting for us to build clever enough experiments to see it.
And for everyone listening, this isn't just, abstract stuff for physicists and labs. Understanding and potentially harnessing these anyons, this frontier of quantum matter, it could genuinely reshape technology and how we interact with information down the road.
Which really makes you think, doesn't it? We found this in-between state for particle statistics, challenging a binary we thought was fundamental. Where else might we find these in-between phenomena? Not just in quantum physics, maybe, but in other areas where we currently tend to see things as just two opposing options, two poles. What other potentials are hiding because we're only looking at the extremes and not the spectrum in between?
That is a mind-bending thought to end on. What else are we missing by seeing the world in black and white? Thank you for joining us on this deep dive. Keep exploring, keep asking questions, and keep digging into the incredible universe around us. We'll catch you on the next one.